all are safe and healthy. Let's continue our discussion from last time. We started talking about dynamic analysis of CMOS inverter. Everything is based on CMOS inverter. Everything. So when we go into what? Studying the dynamic properties or the noise margin or the sizing, or so, we will always compare the actual logic with a what? With an inverter. Clear? With an inverter. So dynamic analysis, this is calculation of propagation delay. What is the goal? What is the goal about the propagation delay? To make it high or low? Low. So goal, minimize propagation delay, which result in what? Increase the speed of the gate. Clear? Increase the speed of the gate. Switch the switching speed. Clear? Okay. Now, let's first of all define what we mean by the propagation delay. This is the input. Let's assume the input goes from what? Low to what? High. And then back to what? Low. Yes? Look at the output. What is when the input is low? When the input is, remember it's an inverter. When the input is low, what is the output? High. Then what? The input goes high. This one will begin to what? Will begin to discharge. Yes? Then what? When the input goes low again, this one will begin to what? Charge again. Did you get it or not? Now let's assume this is what? VDD. Yes? The point or the time it takes to drop to what? VDD over 2. Yes? This one is called what? From here to here. We call it what? VP high to low. Did you get it? Okay. And similarly, this time is called what? TP LH. Auto. Clear? And again, as I told you last time, TP HL and TP LH need not be the same. They don't need to be the same. They will be the same if the CMOS pairs are what? Symmetric. And one more time, what does symmetric mean? W over L N, K N prime, is equal to what? Yes? And what else? DTN is equal to what? Absolute value of what? VTP. Remember, VTP is negative. So when you take absolute value, it becomes what? Becomes positive. Clear? Okay. Any questions so far? Any questions so far? Okay, so let's see if you can help me. Let's start first of all with, by the way, what is TP total? TP is what? The average of the two. Clear so far? No response. Clear so far? I use the average of the two. By the way, if they are equal, then what? Then TP is the same as either one of them. Did you get it or not? But if they are not equal, you take the what? You take the average value. Okay, let's look at this one first before we get to the CMOS. And let's stop again one more time for just a second and try to understand where this C came from. This capacitor. This capacitor C is the result of what? Result of the three components. What are they? The first one, parasitic. Within what? Within the device. Why there is a parasitic capacitor? Remember the gate, a plate, you are going to apply positive voltage, and the N channel that is enhanced, that you are going to create, is a negative. So what did you create? Two plates, one of them is positive, the other one is negative. What separates them? SiO2, which is a dielectric. Did you get it or not?
Yes.
No response. Yes or no?
Yes.
You created a what? A capacitor. Clear?
Yes.
That's a capacitor. Parasitic capacitor within the device. Wiring capacitor. Clear? Why? So what does it mean? When you design or when you fabricate your circuit, make sure all the wiring are what? Long or short? Short, very short. So that their contribution to the total capacitor is very little. And then what? Input capacitance. Or the fan out gate. Gate, sorry. What does fan out mean? That's an inverter. I have an inverter. Yes? How many what? How many gates can it what? Can it drive? Are you following me or not? Each one of them has an input capacitor. By the way, what does this one put a limit? He put a limit on what? On the fan out. Because more what? More gates, logical gates are driven by this inverter, the capacitor will what? Increase. Why? Because we know capacitors in parallel becomes what? Higher or lower? Higher. You follow me or not? That puts a limit on how many what? That puts a limit on how many what? How many gates you can what? You can drive. This fan out. Let me jump a little bit ahead of my time. How about the fan in? What is the fan in? I have a gate. What is the beauty of the inverter? The beauty of the inverter is has how many input? One input. Any other gate has at least what? Two inputs. And remember, for every input you add, how many transistors do you need? You need two. One in the NMOS and one in the what? PMOS. You losing me?
No.
For every input you add, you need what? Two transistors. Which means what? It means the area will become what? Larger and larger. Yes? Capacitance will go what? Up. Did you get it or not?
Yes.
No response. Did you get it or not?
Yes.
What is the capacitor proportional to? Capacitor proportional to what? Some epsilon naught, which is the permittivity, times what? A divided by the distance. Did you get it or not?
Yes.
What is this A? That's the area. So the larger the area, the capacitor is what? Is higher. Now, the L, I want you to look at the distance. This is the length of the channel. The length of the channel, yes? The higher it is. Sorry, this is the distance between the what? Between the plate, not the channel length, I'm sorry. Distance between the plates, yes? The what? Thinner, what happens? This one will go up as well. Clear? Okay, so keep that in mind. We'll get to all of these in just a second. This is the input. This is the what? Output. Yes? Now, this is the what? Resistive loaded. Yes? What did we saw in the resistive voltage? Do you remember? What is VOH? VDD. Was that good or not?
Good.
That's good. VOL. Was that zero or not zero?
Not zero.
Not zero. So initial. Let's assume what? Let's assume that the input was what? High for a long period of time. Yes? What happened to the capacitor? The capacitor discharged through the what? Through the NMOS. Yes? To what value?
Not zero.
To what value?
OVOL.
Huh? A VOL. It cannot reach what? Zero. Because VOL is what? It's a minimum. Did you follow me or not?
Yes.
Yes or no?
Yes.
Now, suddenly, the input goes what? Low. So the input was what? High, and suddenly the input goes low. Clear? What will happen?
Charge.
The NMOS is what? Off. Agree? What will happen to the capacitor? The current, by the way, will go this way. Can it go this way? No. Why? Because the NMOS is off. So it goes this way. What happened to the capacitor? Begin to charge. What? To what value? VOH, which is what? VDD. What do I want? I want what? How long does it take the charge to reach half point between what and what? VOL and what? VOH. So what do I say? V9. Remember the equation I gave you last time? The final value, what is the final value? Yes or no? No response. Yes or no?
Yes.
Okay. Next. Plus VOH minus what? VOL, yes, E to the minus what? T over what? RC. RC stands for what? Time constant. Did you get it or not? This tau from what? From ECE 340. Did you get it?
Yes.
That's the output voltage. Now, let's see if you can help. As t approaches infinity, what will this term approach?
Zero.
Right? This one will approach what? Will approach zero. Agree? Okay. So, oh, sorry, it's minus. Sorry. What will this one approach? Zero. What is the final value? V naught is VOH. Yes? At d equal to zero, what is this? What is this at d equal to zero? 1, which means what do I get? VOH minus what? VOH cancel, and what do I end up with? Which is what? Which is the initial voltage across the capacitor. Did you get it?
Yes.
Lost me here? One more time. What am I assuming? The input was what? High for what? Long period of time. Yes? NMOS is what? On. Capacitor is what? Discharging. To what? Cannot reach what? Zero. I would like it to reach what? Zero. But it doesn't. It reaches what? VOL. Suddenly, the input became what? Low. Agree? The NMOS become what? Off. Current goes this way. The capacitor begins to what? Charge. Through who? R. To what value? Which is what? Which is VOH. Agree? So the final value, VOH, minus the final value minus the initial value, E minus E over RC. Did you get it or not?
Yes.
Yes or no? Then what do I need? I need to get the propagation delay. Yes? What do I do? By the way, what is this? What am I calculating? The propagation delay what? From what? Remember, what did I assume? The input is high for a long period of time, which means what? The output is what? Low. Yes? So what am I calculating? T, B, L, H. Did you get it or not? Yes or no?
Yes.
Good. Help me. What do I do next?
You make
What do I plug in V naught? I plug what?
VDD.
1/2 VOH plus what? What is that? When I say 1/2 VOH plus VOL, what am I looking at? Midpoint. Did you get it or not? Midpoint. In other words, think about it. Average value. Yes? How would you get the average value? If I give you two numbers and I tell you what is the average, what do you do? Add and divide by 2. That's what I did. Clear? And what is this equal to? VOH minus what? VOH minus VOL. E, look at what I like, minus. T, P, the thing that I want. LH over what? Stop. Did you get it or not? No response. Did you get it or not?
Yes.
From this equation, I will get what? We get T, P, L, H, whatever it is you can do. By the way, everything is known. Known. RC is known. This one is there. Yeah.
Over there, the point is listed as VDD over 2. Is that only for CMOS?
This one. This one is for the CMOS.
Okay.
Because the CMOS reaches what? The VDD, the VOH is how much?
5.
VDD, and the VOL is how much? 0. So when you add them together, you divide by 2, you get VDD over 2. But this one does not reach, VOL does not reach 0. Clear?
Clear.
No response. Clear? Now let's get to the CMOS. Did you understand this? By the way, you can do also the same thing with the what? With the high to what? High to low. Clear? Which means what? When the input, what? Goes what? High again. Yes? This one will begin to what? Discharge. Clear? Good. Now, let's look at this. This is QN. This is what? QP. Okay. Let's start first of all verbal. Verbal. If what? If Bn is high, what can you tell me about this? On. What can you tell me about this? What will happen to the capacitor? Well, what? Discharge through the NMOS. Did you get it or not?
Yeah.
Yes or no?
Yeah.
What? When I say discharge through the NMOS, where? Well, by the way, do you see the resistor? Yes, there is. Because this is in a which mode?
Saturation.
Triode mode. Did you? What did you say?
Oh, sorry.
What did you say?
I said saturation.
No saturation in 442. In 442, we are going to go what? Only in the what? Cutoff and the what? The triode region. We are not going to work in the saturation region. We want to make the saturation as what? As narrow as possible. Oh, good. So what does this one behave as? The on resistance, which is what? R, D, S, N. Yes? Yes? Did you forget what is this equal to?
I forget.
Did you forget what is this equal to? Right to the end. Is what? Yes? And then what? That's a resistor.
Yeah.
Yes or no?
Yes.
Okay, what do I want to make the resistor? High or low?
Low.
Huh?
Low.
Low. Why? Because I want the discharging to be what? Very quickly. Do you follow me or not? Okay, I want you to look at this and tell me what does it depend on. This RDS. Let's see. W, if you make W smaller, first of all, let's look at the L. What do I want to make L? Huh? Concentrate. Concentrate. If L is small, W over L is what? Large. RDSN is what?
Small.
Small. Because it's in the denominator. Yes or no? Now do you see why the sizes for the channel reduced over the years? It was in the what? In the micrometers then, and now it's nanometers and so on and so forth. Did you get it or not? They want to make this one what? Smaller and smaller, so that what? The time constant become what? Smaller and smaller. Agree? How about W? How about W? What do I want W to be? I want also to be what? Large. Yes? We have a dilemma here. What is the dilemma?
It makes more capacitance.
If you make W large to make what? RDSN small, making W large will increase the what? Capacity. The capacitance. I said capacity. I'm sorry. The capacitance. You lost me here? Did you lose me? It will increase the what? The capacitance. Clear? But we'll get to that in just a second. Okay, so it will discharge. Yes?
Yeah.
When this one goes low, what will happen? Off,
Off.
on. What will this one?
Charge.
With what resistance? The on resistance of this one, which is this one. Clear?
Yeah.
No response. Clear? Good. Now, let's understand how we calculate the propagation delay. I shall take, we shall consider the input to be low and at t equal to 0, the input goes what? High. Clear so far? No response. Yes or no? Let's see what happens. This is VD versus what? ID. Something like this. Yes? Yes? Now, initially, what am I saying? The input is what? Low. What can you tell me about this? Open. What can you tell me about the voltage across C? VDD. Because why? I'm assuming that the input was what? Was low for what? Long period of time. Did you get it or not? At t equal to 0, the input became what? High. Clear? Yep. So where are we? At t equal to 0 minus. Where are we? By the way, what are these curves? What are they? VGSN, which is what? VN. Did you get it or not? Okay, good. Initially, where are we? At point A, what is the voltage? VDD, which is what? VOH. Did you get it or not? Yes or no? Yes. Why? One more time. What am I assuming? At t 0 minus. Would you answer what 0 minus mean? Just before what? T equal to 0. What was the input? What is the output? High. It's an inverter. Yes? This is the output. Help me now. At t equal to 0. Yes? What happens? The input became what? High. But what is the input? What is the input? VGSN. Yes? Where do I go? From where to where? I go from here all the way to what? Here. What is this? VGSN equal to what? VDD. You cannot go more than VDD. Did you get it or not? This is at what? Point B at T equal to what?
0 plus.
0 plus. Losing me? Losing me? Okay. What can you tell me about the NMOS? The input went high. The NMOS start what? On. Yes? This one is what? What happened? The capacitor will begin to what? Discharge, which means the voltage across the capacitor, which is the same as the drain voltage. That's the drain voltage of the NMOS. Yes or no?
Yes.
Goes what? Where? Show it to me. Can you show it to me? It's on this, and I'm going to what? I'm going to move. This one is not escaped very nicely, but let's say this. Yeah. Yes? I'm going where? This one. Yes or no? Which mode is the transistor? Look at it. Which mode is the transistor? This one. Look at the diagram. Saturation. Did you get it or not? But does it remain at that saturation? Why not? No. When does it begin to what? To enter the what? The triode mode. When? When the voltage at D goes below what? VDD minus what? VT. Did you get it or not? Why? No response. Remember the saturation and the triode? Yes? When will the channel get pinched off? Do you remember the pinch off? When will the channel be getting pinched off? When the voltage at the drain is what? Higher than the voltage at the what? At the gate by how much? By VT. In other words, V drain is what? Greater than what? VDD minus what? VTN. Did you get it or not? So if it is greater, which means what? We are in the saturation. Yes? But once we get to this point, which is what? VDD minus VT, the drain is coming what? The drain voltage is reduced. Yes? Which means what? The channel is back to what? Open. No pinch off. Did you get it or not? Where am I entering? I am entering the triode region. Yes or no?
Yes.
Until I reach what point? So let's say this one is point C. And let's say this continues until I reach what? This point in which what? The voltage at the drain is what? VDD over 2. Did you get it or not? You lost me here. You lost me. Can we try it one more time? Can we try it one more time? Remember the NMOS. To create the channel, yes, VGS needs to be greater than what? VT at every point along the what? Along the channel. Did you get it or not?
Yes.
But as I increase the drain voltage, the difference between the gate and the drain is going to fall below what? VT, causing the channel to what? Pinch off. Yes or no? When will this happen? When VD is greater than what? VDD minus what? VT. That will cause the channel to be what? Pinched off, and the transistor to operate in a which mode? Saturation mode. Did you get it or not? Yes or no? So all of this, from where? From VDD to what? VDD minus VT. During that time, which mode are we? Saturation. Why? Because the drain voltage is greater than what? VDD minus what? VT. Do you agree? But as it discharge more, you are going to fall below VDD minus VT. Yes? Which means what? The channel is back what? Back what? Uniform. You follow me or not? No pinch off. Agree? Which means you entered which mode? Where? Show me the trial mode. That's the need. Did you get it or not?
Yes.
Keep what? Keep discharging the capacitor until it reaches what? VDD over 2. That's what we want. Clear? So the question is what? How long does it take the capacitor to go? By the way, will it take time from here to here? Here to here. At t equal to 0 minus to t equal to 0 plus. Does it take time? 240. The voltage across the capacitor cannot change instantaneously. Rings a bell or no bell? Rings a bell or no bell? Capacitor, the voltage across the capacitor cannot change instantaneously. The current can change instantaneously, but not the what? Not the voltage. Clear? What was the voltage here? VDD. What is the voltage here? VDD. You follow me or not? Cannot change instantaneously. So how long does it take the capacitor to go from point B to point what? C. No. To point what? D. Clear? That is called the what? The discharging current. The discharging current. Agree? But, yes.
Oh, sorry, point D is VDD over 2, right?
Cannot hear you, my dear.
Point D is VDD over 2?
Point what? D is when the output, the drain is what? VDD over 2. That's how we define the propagation delay, right? When the voltage across the capacitor reaches what? 1/2 the maximum. Clear? One more time. What is VOL here? In the CMOS. CMOS inverter, VOL,
0.
VOH. What is the half point? VDD over 2. This is VDD over 2. Yes? I need to find the discharging current. But I have a dilemma. What is the dilemma? From point B to C, the discharging current is what? The saturation current. You lost me? Did you lose me? But from point C to D, it's what? Triode current. These are different equations. Did you get it or not? Yes or no?
Yes.
I need to calculate the current in each one from B to C, and then what? From C to D, and what do? I take the average. Did you get it or not?
Yes.
No response. Did you get it or not?
Yes.
Okay. So going from what? Discharging current. I'm still waiting. I'm still waiting. It's operating in the saturation mode. Yes? Saturation mode. Still waiting. What goes in the equation? Nothing. Didn't I ask you to write the equations on a cue card? Did I ask you to do that or not? What happened? It went from one ear, it came from what? The other ear. I asked you, I told you, write the equations for the what? Saturation and the triode and the cutoff for both the NMOS and the what? PMOS. Did I ask you to do it?
Yes.
Did you do it? No. Am I surprised?
No.
No, I'm not surprised. Not surprised. You just want to come to the class. This is what you want. You want to come to the class, and that's it. You don't want to do anything else. Just come to the class. And you expect to what? To clear the class. I have a news for you. Make a plan to take it again next semester. And unfortunately, you will be stuck with me again. Nobody wants to teach 442. So they assigned it to me again. What is the equation? Give it to me.
1/2.
This is 1/2. I already wrote. What is this? VGSN. What is VGSN? What is it? VDD. So it's what? VDD. Continue.
Minus VT squared.
Agree?
Yeah.
No response. Agree? Okay. Now, from what? C to what? To D. Transitor is in which mode?
Triangle.
One more time. Why? I want you to look at the diagram and tell me why it is in the triode mode. What does the VD reach? VDD minus T. If it continues, it's getting what? Lower than VDD minus T. Yes? Is the channel pitched off or no more pitched off? No more pitched off. We go to the triode mode. Give me the equation for the triode mode. So what is it? Kn?
KN
prime
over
W
2.
VGS minus VT
VG?
VGSN.
What is it? VGSN. Still what?
Oh, VDD.
Why? I am moving around the same circle. I'm sorry, same circle. I'm moving around the same graph. Yes? So what is it?
VDD minus VTN.
Multiply.
VDS.
What is it? What is a VDS?
BO.
Huh?
BO.
I know be out. What is it? See, I need to put something. This I'm calculating the current. Clear.
Clear.
No response. Clear. Clear. This is the what? This is the VDS at point what? C. Clear?
Yeah.
Okay. Now, what is the average current? Let's call this one I1. I, what is it? DC. And what is this? ICD. Yes? So, the discharging current? I is what? I, help me, CD. Which means what? I add this plus this, and I divide by what? By 2. By the way, is this a crude? Is this a crude approximation? I mean, average current. Yes? Yes or no? How is the current changing? I'm taking the what? I'm taking the average value. Clear? Then what do I say? Remember, by the way, C, delta B, C is the capacitor. Delta B changing the voltage. Yes? Equal to what? Equal to T, P, what is it? What are we calculating here? No, I know. What is it? High at T equal to 0. What was it? VDD is, so it's what, high to low? Yes? Times what? The average current. Yes or no? What do I put here? What do I put in delta V? Where did I start? VDD. Where did I end? What VM? Where did I end? VDD over 2. So. Yes? No response. Yes?
Yes.
This is what? C multiplied by the voltage equal to what? Average current. What am I going to plug? This plus this. Divided by what? 2. I will plug it there. And what is the only unknown? The only unknown is TPHL. And you got TPHL. Alpha N. C over Kn. W over L. N times VDD. Yes? No response. Yes?
Yes.
And alpha N is equal to 2 over 7 over 4 minus 3 VTT, VT over VDD plus VT over VDD, the whole thing square. When I say the whole thing, only this term is square. And then what? Close the bracket. Did you get it? No response. Did you get it? One more time. One more time. How did I get this? How long does it take you to what? The capacitor to discharge from where to where? From VDD to what? VDD over 2. How long does it take? Clear? That's this one. TPHL. Going from high to what? Low. Clear? What is the current? The discharging current. The discharging current is the average of 2 currents. Why it is average of 2 currents? Because when you go from B to what? C, it is what? Saturation current. From C to D, it is what? Triode current. By the way, which one is higher? Of course, the saturation current is higher. So saturation current, and then what? Triode current. Agree? So we calculated each one of them, and then what do? I add them and divide by what? 2. I plug it here. Did you get it? Now on this side, what is it? C delta V. Did you get it or not? By the way, what is this equation? Can you tell me what this equation? What is the current to a capacitor? What is the current? Equation of current? How would you relate the current in terms of the voltage across a capacitor? Oh God, heaven. 240 guys. If I have a capacitor, what is the relationship between the current and the voltage? Is it Ohm's law?
No.
So what is it? It's what? I of T? I'm stunned. Yes or no? No response. Yes or no?
Yeah.
This, what am I doing here? This C is this C. Yes?
Yeah.
Delta dV by dt. This is the V. Delta V, if you put this time here in the denominator, remember we started at what time? 0. Where did I end up? TPLH. Yes or no? Sorry, TPHL. Yes or no? As the current. This is coming from here. Did you get it or not? No response. Did you get it or not?
Yes.
Okay. I calculate this, I get this one. Alpha and C over this. And the alpha n is this. Clear? This is how you calculate the propagation delay, high to what? Low. Now, similarly, I'm not going to repeat the analysis, I'm just going to write the equation. What is the analysis? Analysis is that when you what? When the input changes from what? Low to high again. Yes? What will happen to the capacitor? Capacitor will begin to what? To charge. Did you get it or not? Through who? Through who? Through the PMOS. Did you get it? Which means what? It means TP LH is equal to what? Alpha P, exactly the same equation. C over what? K P prime. W over L P times what? VDD, where alpha P is equal to what? 2 over 7 over 4 minus 3, look how I write it, absolute value of VTP over what? VDD, and then what? Plus absolute value of VTP divided by VDD, the whole thing what? Close the bracket. Clear? No response. Clear? This is exactly the same as this one, except for what? VT is absolute value. Why? Because VT for the PMOS is negative. You need to take the absolute value. Yes? Yes? Okay. And this one is what? KP prime W over LP and so on and so on. Now, if the two transistors are symmetric, this is the same as this. Did you get it or not? No response. Yes or no?
Yes.
Now, let's understand this equation. And let's understand what are the factors that will what? Remember the goal. What is the goal? I want to minimize this. Yes or no? I want you to look at the equation and tell me. What do I do first? About L. Make L what? As small as the technology what allows it. Did you get it or not?
Yes.
And if you look at the charts in the first lecture, you will see the length of the channel is going what? Down, down, down. Started in micrometers, now it's in what? Nanometers. Fractions of a nanometer. Do you see why? Why? One more time. Why? The lowest L, what does it mean? The denominator is what? Larger, which means this one is what? Smaller. Did you get it? Yes or no? Good. Now, what about C? What do I want about C? I want to make it what? Smaller. What does that mean? When I lay out my logical gate, I make sure that the wires are what? Are small? Yes or no? W also is what? I want to make W what? I want you to look at this. What do I want to make W? I want to make W large. Why? So that this one becomes what? Low. But I have a dilemma. If you make W large, what you are also increasing? You are increasing the capacitor. You lost me here. Did you lose me? Is that a contradiction? That's a contradiction. I want to make W large so that this one becomes what? Small. But making W large, it will increase what? The capacitor. Yes or no? Which capacitor? It will increase which capacitor? Remember, how many sources for the capacitor do we have? 3. Parasitic, wires, fan in. Sorry, fan out. Yes or no? What will that affect when you increase W? It will increase the parasitic capacitor, but it will have no effect on the what? On the other two components. Did you get it or not? Yes or no?
Yes.
So you need to what? You need to balance whether the increase in W, which will result in increase in C, is better or what? Or worse. Well, depending on which component is the dominant component. Clear? Yes or no? And one final thing. How about VDD? about VDD? Do I want to increase it? Yes? I want to increase VDD. Dilemma. What is it? Increase the VDD? I'm going to increase the power dissipation. Yes or no? The trend is to go what? Lower in VDD. You follow me or not? To conserve the what? The batteries. They started with what? They started with VDD around 15 volt. Currently is what? 0.8 or 0.9 volt. From 15 all the way to what? 0.9. Why? Why? They want to limit the power dissipation. You tell me, Professor, but didn't you say the power dissipation in a CMOS equal to 0? Why? Because when this one is what? High, this one on, this one what? Off. And vice versa. Did you get it or not? We are not talking about the static power. We are talking about the what? Dynamic power. You follow me on that? What is the dynamic power? When the what? When the inverter is switching from what? Low to high or what? High to low. Static means what? It's either what? High or what? Low. I don't have a problem with static power. Why? Because it's equal to what? 0. You lost me? Did you lose me? Why is there power dissipation during dynamic operation, during the switching? There is current passing through the what? Through the transistors. Otherwise, how will the capacitor charge and discharge? You lost me. Did you lose me?
No.
You lost me. There is no question in my mind you lost me. During the charging and the discharging, is there current passing through the devices?
Yes.
That results in what? Power dissipation. You follow me or not? Yes or no? Which we'll calculate shortly. Clear? Clear? Do you see the dilemma? I want VDD here. What do I want VDD? I want it to be what? High. So that this one becomes what? Low. And one more time. Why do I want this one to be low? I want my devices to be what? Faster. So I will need to make VDD high. But you make VDD high, the power dissipation will become what? Much higher. Agreed? Now you might tell me so. So on a single chip, you are going to have what? Billions of what? Millions and millions of what? Of these transistors. The total power dissipation might exceed what? 100 kilowatt. Did you follow me or not? We are talking about million and million. We are not talking about one transistor. Did you get it? Yes or no? Remember I showed you in the first lecture, which you forgot, a picture of a chip, which is what? Burning. You forgot this? You forgot. A slide. Check it back if you want you go home. Check it. I put a slide in which what? The chip begins to what? Burn. Why? Because the power dissipation is what? Power dissipation as what? Where is the power dissipation? As heat. You agree? Which means what? The temperature? Go on. Clear? That's a dilemma. And the design of what? And the design of what? The dynamic operation of the CMOS. There are many contradictory what? Many contradictory components that you need to take care of. The whole idea is what? Is that you have to remember that C is a function of what? Of a 3. If you make your wiring properly when you lay out your circuit, yes. If you limit the what? The number of what? Number of gates is driven by this inverter, limit them. Yes. Also limit the number of input. Question. NAND gate. Suppose I have 2 input NAND gate. Yes? Could I have 10 input NAND gate? When they design it, they don't design it as a what? 10 input NAND gate. They design it as a what? Cascaded number of what? Gates? Yes? Yes or no? No response. Yes or no?
Yes.
Which means what? If you do have, for example, 3 input NAND gate, design first of all a what? A 2 input NAND gate, and the output combine it with the what? with the third one, such that the overall is equivalent to what? A 3-input NAND gate. But in this case, what did you use? You used what? A 2-input NAND gates. Did you get it or not? Remember, for every input, you are going to add how many transistors? 2 transistors. I will show you that in just a second. Clear? No response. Clear? This is what? This is the dynamic characteristics of the transistor. Clear? Now, all what you need to do is to know where to plug in the equation. So the question in the homework I will assign tomorrow, several questions deal with this. You just need to what? You just need to know how to plug. Clear? Good. Next topic, which is also included. We'll get to the power after we finish this one. Sizing of logical gates. In other words, how do we choose W over L and W over L P? Clear? That is called the sizing of the transistor, of the gate, logical gate, transistors and the logical gates. Now, let's see if you can help me here. Remember, by the way, if symmetric, what do I have? If symmetric, W over L, Kn, so Kn prime. N is Kp prime. P. Clear so far? Okay. Now, we choose L to be what? By the technology. Did you get it or not? Yes or no? So for example, by the way you hear the power. They tell you what? For example, 90 nanometer CMOS. What is that 90 nanometer? That's the L. Did you get it or not? 45 nanometer, 13 nanometer. That tells you L. So what does that tell you? It tells you choose L for both the NMOS and the CMOS, for the NMOS and the PMOS to be the same and to be the what? The minimum allowed. Clear? Why minimum? One more time. Why minimum? Because if L is minimum, this one is maximum, this one is what? Minimum. They become faster. Clear? Now, so what remain is the areas. W and, now Kn is equal to what? COX, capacitance of the oxide, times what? Mobility of the electrons. Clear? Kp, COX, times mobility of what? The holes. Which one faster? The holes or the electrons? Electrons are faster. So UN over mu P, mu N over mu P is what? Kn prime over what? Kp prime. In other words, if I divide this by this, the COX cancel and I end up with what? Mu N, mu P. Did you get it or not? And this is around what? Which means what? This ratio is around what? 2 to 4. Did you get it or not? Which means what? If I want this one to make it symmetric, yes? If I want to make it symmetric, which I emphasize, not necessarily the optimum thing to do. Not necessarily the optimum thing to do. Clear? But let's assume I want to make it symmetric. What does it mean? This should be what? Equal to this. Kn prime over KP prime is equal to what? W over L P over what? W over L N, yes, equal to what? Mu N over what? Mu P, which is roughly what? 2 to 4. Did you get it or not? No response. Did you get it or not? Where did this come from? Tell me, where did this come from? Look at the equation here. Yes? What is omega n? Sorry, mu n over mu p. Mu n over mu p is what? Kn prime over what?
KP prime.
Which means what? Kn prime over kp prime is what? Mu n over mu p. What remain? Omega over L, sorry, W over LP over what? W over Ln. Clear? Oh. Now, instead of writing these things, denote W over LP by just what? P. For simplicity. Did you get it or not? No response. Yes or no? So that I don't keep repeating what W over L, W over I just denoted by P. And W over L, N denoted by what? N. Clear? So what does this one tell you? I tell you P is approximately what? 2 to 4 times what? Clear so far? No response. Clear so far? So now what do I have? I have an inverter. I'm going to choose this to be P and this one to be what? N. Clear? No response. Yes or no?
Yes.
By the way, if I make N equal to P, if I make N equal to P, what am I minimizing? What am I minimizing? If I make N equal to P, by the way, N is not equal to P. P is roughly what? 2 to 4 times N. But if I make P equal to N, what am I minimizing? I'm minimizing the area. Why? Because the area is what? W times what? L. Yes? Yes? So if I say what? The NMOS, the NMOS and the PMOS have the same what? Have the same, if N is equal to P, what does it mean? The length is the same, it means their width is what? The same. But if I say P equal to what? 2 to 4 times N, what does it mean? It means the area of this is what? 2 to 4 times bigger than the area of this. Clear? So if N equal to P, area is what? Minimized. By the way, is that good or bad? That's good. Did you follow me on that? So that I can what? I can squeeze more what? More transistors into the what? Into the same chip. Did you get it or not? But we will see that N does not equal to P. Did you follow me on that? Why? Because the mobility, again, as I told you, mobility of the electrons and the mobility of the holes are not the same. Clear so far? So then what do? I set up the inverter. N and what? P. Clear? I calculate the overall C. I model it as a what? As a parallel capacitor. Yes or no? What will I have? I will have a what? A charging current, where the charging current through who? Through P, and a discharging current through what? N. Clear so far? Yes or no? That's for the inverter. And I'm going to what? I'm going to use it as a benchmark. For what? For other logical gates. So if I want to design, for example, a 2-input NOR gate, just an example, or a 4-input NOR gate, or NAND gate, clear? What do I want? I want to choose the N and the P for those gates, the NAND and the NOT, such that the charging and the discharging currents are the same as what? As the inverter. What does that mean? What does it mean? It means I want to find what is the worst case scenario for the combination of the input that will result in what? In the same discharge and what? Charge current. By the way, if the same discharge and charge current are the same as the inverter, what is the worst case scenario? The worst case scenario is the what? The propagation delay for the gate, any gate, will be the same as who? Will be the same as the inverter. Did you get it or not? If I make the charging of the charging current and discharging current the same, it means, by the way, what am I also assuming? I'm assuming C is the same. Well, you cannot assume that, but just an assumption. Did you get it or not? No response. Did you get it or not?
Yes.
Oh, so now what do I need? I need the following. If you are going to design a logical gate other than the inverter, yes, you are going to have at least how many inputs? 2 inputs. Yes? And the transistors are going to be connected in what? Remember the PDN and the PUN? PDN, all what? NMOSes that are either in what? Series or what? Parallel or what? Combination. Did you get it? Same thing with the PUN. Did you get it or not? Now what I want to show you is what? When you do have transistors that are in series. So let's assume that I have a transistors in series. Yes? The first one, W over L1. Second one, W over L2. Yes? And they are in series. These are both NMOSes. Yes? They don't need to be NMOS. They could be PMOSes. Yes or no?
Yes.
I would like to find what is the equivalent W over L? What is the equivalent W over L? Which means what? I want to find what is the equivalent of this, in other words, replacing the two by only what? One of them. In exactly the same way as we did when we have two resistances in series. If I have two resistances in series, R1 and R2, are they in series? Yes or no? What is the equivalent? R1 plus R2. Exactly the same thing here, but I'm talking about what? What is the equivalent? W over L. Did you get it or not?
Yeah.
Because I want to replace the whole thing by just what? To make it similar to who? Inverter. Did you get it or not? Oh, good. Now, what is the resistor in here? The on, when they are, by the way, what is the worst case scenario? What is the worst case scenario for these two? Both of them are what? On. Why? This is the worst case scenario. Because if both of them are on, what will happen? What will happen is that the total resistance will what? Go up. Did you get it or not? Which means what? The discharging will take what? Longer. Did you get it or not? Okay. I want the equivalent of this. What is R on of this one? R on of this one, which I erased it, was what? What was it? 1, where is it? Where is it? Yes. Yes? All of this constant. So I'm going to say what? It's proportional to what? K1 over what? Agree?
Yeah.
No response. Agree? What is the K1? K1 covered all the other constants here. Yes? Second one. Agree? Let's say same K. Same K. Yes? Add them together. What do I get? No, what am I doing? Jeez. K. Yes?
Yeah.
Yes?
Yes.
But what is RDSN? This is a total. This is a total. This one is equal to what? K times what? Equivalent. You agree? Agree? No response. Agree? What do I get from here? What does this resemble? Parallel resistances. Do you follow me or not? So what do I conclude? Series transistors, if you put series transistors, the overall W over L is calculated equivalent to the way you calculate resistances in what? In parallel. Did you get it or not? No. I ran out of time. Next time we'll continue. But answer me the following question. Answer me the following question. What if I have this? What is this? W over L? 1, W over L? 2. What is the equivalent? Huh? In series. The equivalent of this one is what? W over L equivalent equal to what? Agree? Conclude for me. When you connect the what? When you connect the devices in parallel, the equivalent W over L, you find it by treating what? The configuration as if they were what? Resistances in what? Series. Which means what? W over L1 plus W over L what? 2. If they are connected in what? In series, then to calculate the what? The W over L, the equivalent W over L, by treating them as if they were what? Resistances in what? Parallel. Clear? Okay, before I let you go. No, I have one more minute. Answer me the following question. Let's assume this is 4N, 4N. Yes? What does that 4N mean? Means this one is 4 times as wide as what? As this one. Did you get it or no? Yes or no? Oh, that's 2N, 2N. Agree? What is the equivalent? N, which is the same as this one. Did you get it or not? I want to make what? I want to choose the sizing of the transistors in a general logical gate to be equivalent to what? To the sizing of a basic what? Inverter. Under what? The worst case scenario. In other words, under the worst case scenario, the delay, the propagation delay, through an inverter and through a what? An arbitrary logical gate is what? The same. Under what condition? Worst case scenario, which means what? Under scenarios which are not the worst case, which one will be better?
The arbitrary gate.
The logical gates. Did you get it or not? Under the worst case scenario, I want them to be what? I want this configuration to be equivalent to what? To this. Yes, under worst case scenario. But if the scenario that's occurring is not the worst case, this one will be what?
Faster.
Better than this one, provide lower delay. Clear? You lost me totally here, but I ran out of time. Next time I will show you with example. Did you get it? Everything is compared to who? To the digital CMOS inverter. Everything. Clear?